ABC. Here's a little screencast to catch both of my periods up on sequences before you start your homework post-test. Just want to make sure that we're both on the same place because I know there was a lot of notation in there. And you've seen I've decided to join the year 2023, and hopefully we'll start using OneNote consistently for this unit. As long as I can get the smartboard in the upstairs room working correctly. Okay, so we saw that we had this notation for an infinite sequence the other day, with these sort of limits on these indices on the outside, right? With 1 and infinity, right? And that's just said that we're going to start indexing these terms at 1 with all sequences, and then we're going to go up forever, right? Denoted by the dot dot dot. Right, so this sequence, right, could have some properties like a sub 1 is 5, a sub 2 is 8, a sub 4 is 14, and so on, right? And we can come up with explicit and recursive definitions for this sequence, right? So if we think about this, right, the explicit definition is going to say, hey, I want to rule in terms of n for the nth term of my sequence, or in terms of k for the kth term of my sequence. And if we think about what that would be, right, we could say that a sub k over here is going to be 5, right, because it's sort of where we start, like sort of you can think of the y-intercept or something of that sort, right, plus 3 in terms of the slope, right, each one goes up by 3 plus 3 times k minus 1, right? We have to sort of index things because 5 isn't the true y-intercept, right? 5 is really the place where k is 1. And so you can try this for any of our values in our sequence over there. And you'll see we'll go up by 3 pretty nicely. If we were to define this recursively, right, recursively requires a base case and an n in terms of n minus 1, or in terms of previous terms, right? So my base case for my recursive definition, base case would be that my first term would be a sub 1 is 5, and then my nth case, right, my kth case would simply be that, oh look, the kth term is simply the last term I had plus 3, right? And so any term we're saying, right, like the fifth term is the fourth term plus 3, and obviously that's true. This is good for some sequences, but for this one, right, we'd have to calculate all of the previous ones, so that might be somewhat cumbersome. So we might not want to think about that as much. So we saw these things, and we were pretty happy, and we could find the nth term of things, pretty easily. But then, we're gonna end up summing these guys and sort of talking about them. I wanted to just motivate that. So we're gonna say that just a definition thing, right? A sequence converges, right? Exactly when you think it would, right? If the terms as k approach infinity, if the terms all approach some single limit, right? So this one up here, obviously this one would go up to infinity, right? But if we had something, like if I had a sequence defined by a sub k equals 1 over k or something, right? That infinite sequence, right? So that would be, a sub k would equal these guys, right? Like 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. Right, this guy, right, this would converge going to 0, right? Because every term would sort of approach 0 as k got arbitrarily large. Okay, so I think I did this with my downstairs class. So you guys can sort of skip through this, right? We talked about what happens if we have some sequence, let's say given by a sub n equals n over n plus 1. Okay, so this is sort of a fancy sequence, and I want to categorize this thing, right? So we could find all sorts of things, right? You could pause this and say, you know, what's a sub 4, what's a sub 5? We could do all that, right? This would be, 4 over 5, and this would be 5 over 6, and so on. Okay, and we could look at this guy, and we could categorize this. And it turns out we're really interested in categorizing them as, increasing or decreasing. And you might think that those terms are sort of obvious, but they actually have kind of a silly definition here. Kind of a silly definition. And we have sort of two ways of classifying things as either increasing or decreasing. We sort of have a difference test and a ratio test. I don't really want to call them tests. Difference and ratio, we'll say. Difference and ratios. Whoa, it's a lot of fancy colors. Difference and ratios, right? And so a sequence is increasing, right? And we sort of say that if the n plus first term is at least as big as the nth term. Similarly, it's decreasing, right, if we're getting smaller. Notice the equals sign underneath there, right? Less than or equal to, greater than or equal to. That's sort of an interesting take here. Similarly, we could also show that something's increasing or decreasing if a sub n plus 1 over a sub n is if that's greater than or equal to 1, or similarly if this guy is less than or equal to 1. And I know some of you are looking at this and saying less than or equal to, greater than or equal to. What about a constant sequence, right? What if my sequence is just 1, 1, 1, 1? Well, that silly sequence is actually increasing and decreasing, which is kind of a silly sequence. So, these terms are fine and all, but we really like the two terms that say strictly increasing and strictly decreasing. These are sort of better terms to think about, and those are the exact same as their counterparts above, except without the equal sign. So then we sort of lose that silly sequence, and we make each term be smaller or bigger than the previous one. I don't know why. Some of my ones have hats and some of them don't. All right, so let's go back to our sequence up here. N over n plus 1 is the nth term. And let's discuss whether or not that thing is increasing or decreasing. Okay, so we're going to do is we're going to show in general, right, we can see pretty clearly that 4/5, 5/6, 6/7, right, this is actually, this is increasing, right? Each term is bigger than the previous one. Let's show that it is strictly increasing. So how we would do that is we would take our sequence. So using differences, we're going to do it both ways. Using differences, we're going to show that a sub n plus 1 is greater than a sub n. And remember that my sequence was defined by n over n plus 1. Is that right? N over n plus 1. Okay. Well, it's also clear, sorry, I should have said that, right? This sequence is going to converge to, 1, right? It's going to approach 1 as n gets really large. So it's going to converge and get up to 1. So let's talk about how we would show this. Well, what is the nth term here? The nth term is just this thing. So we know we would have n over n plus 1 on this side. And then, we're really saying, is this greater than, right? Is this greater than? What are we going to have over here? We're going to have the n plus first term. So that's n plus 1 over n plus 1 plus 1, right? Because we're just plugging n plus 1 in up here in for n, right? Plug n plus 1 in for n and I get this thing. Well, that's really saying, hey, is n plus 1 over n plus 2, that's what this is, minus n over n plus 1, is that greater than 0? And if we can show that it is, we know that this thing is strictly increasing, right? Strictly increasing. We're trying to show this is strictly increasing. And so how would I do this? Let's put it over a common denominator. So we multiply this fraction by n plus 1 over n plus 1. And I'd multiply this fraction times n plus 2 over n plus 2. And what is that? That means this thing is going to be n squared plus 2n plus 1, because I'm foiling this guy really, right? Minus n squared minus 2n. All over n squared plus 3n plus 2. Well, what is that top? That top is really just 1, right? Because we have minus 2, n squared minus 2n, right? So this is really 1 over this thing. And since in our sequence, n is always positive, right? Really, sorry, we should have had these guys. Right? Since n is always positive, this thing has to always be positive, right? Because we have a positive 1 over a positive number, which is greater than 0, right? So by the difference test, we can say, oh, look, the n plus first term is always bigger than the nth term, which is kind of obvious. If we wanted to use ratios, we're going to try to prove this thing. Can I prove that a sub n plus 1 over a sub n is greater than 1? Well, we already know what those are, right? A sub n plus 1, that was this thing, n plus 1 over n plus 2. And a sub n, well, that was just n over n plus 1. I want to show this is greater than 1. Well, if we divide by a fraction, that's the same as multiplying by the reciprocal. So simplifying this thing here, I'm going to get what? I'm going to get n squared plus 2n plus 1 over n squared plus 2n. Well, this is fairly obvious, right? These guys are the same, right? And they're positive, again, because n is positive. So because those are the same, and we add 1 in the numerator, right? Upstairs is, upstairs is greater than the downstairs. So therefore, by both of these tests, we only need to use one. This thing is strictly increasing, right? Both of these guys show strictly increasing. Okay? So I think you should now be able to do your homework. We will talk about this more. I know there's a lot of notation. And I hope you guys have a good 3-day weekend.